Beyond Pluto, far past every planet, asteroid, and icy dwarf world that can be mapped, there may be a vast shell of frozen objects surrounding the solar system. No one has ever seen it directly. No spacecraft has reached it. And yet scientists believe this dark region may be the hidden source of the long-period comets that sometimes fall toward the Sun. Tonight, this journey goes beyond the known edge of the solar system and into the mystery of the Oort Cloud. If this kind of deep space exploration belongs on the channel, please like the video, subscribe, and keep travelling deeper into the universe, far beyond the bright orbits of the known planets, beyond the last dwarf worlds that can still be named and mapped. The solar system reaches toward a place that has never been seen directly. At its farthest proposed limit lies the most uncertain frontier still claimed by the Sun. This is the outermost reach of the Oort Cloud, a distant borderland where the Sun's gravity continues to matter, yet no longer rules with the quiet firmness it holds closer in. Here the solar system is not a flat family of worlds circling in a common sheet. It becomes instead a vast and nearly spherical domain, so spread out and so dim that the idea of a region begins to blur into the larger darkness around it. In this far exterior realm, distance changes the meaning of almost everything. Near Earth, the Sun is not only the source of light and warmth, but the unquestioned centre of motion. Far out here, the Sun is reduced to an unusually bright star in a crowded sky. It still marks home, but it no longer fills space with strong command. Its pull reaches outward across immense emptiness, and the outer Oort Cloud is thought to occupy the final stretch where that pull can still keep icy bodies loosely bound. These objects do not cling tightly to the Sun. They remain attached in the weakest possible way. The scale is so great that ordinary comparison begins to fail. The outer Oort Cloud is thought to extend to tens of thousands of astronomical units from the Sun, and perhaps as far as 100,000 astronomical units. At such distances, the Sun is separated from its most remote attendants by a gulf so large that light itself needs many days to cross it, and in some estimates more than a year to pass from the Sun beyond the cloud's farthest proposed margin. The space between one object and the next is not like the crowded image often imagined from diagrams. It is mainly emptiness. If an object drifts there, it moves through cold, dark intervals so vast that the presence of neighbouring bodies changes almost nothing about the immediate surroundings. This is why the region is never described as a solid shell in the ordinary sense. The word shell suggests a surface or a packed layer, but the outer Oort Cloud is better understood as a broad statistical swarm. It is spherical not because it forms a visible ball, but because the orbits of its distant bodies are thought to point in many directions, above and below the plane of the planets as well as around it. At the farthest edge, this spherical form becomes even more diffuse. The Sun's distant population thins into a sparse and almost abstract cloud, a structure defined more by shared gravitational membership than by any visible boundary drawn in matter or light. Its darkness is complete in a practical sense. The bodies there are believed to be mostly small and icy, remnants from the early history of the solar system. But at this outer limit they are too faint and too far apart to light the region in any meaningful way. Sunlight arrives weakly. It does not brighten a landscape. It barely touches surfaces. There is no glowing belt, no broad haze, no luminous rim marking where the Sun's dominion ends. Even if an observer could stand upon one of those frozen bodies, the scene would resemble isolation itself, with one strong star marking the Sun's position and countless others surrounding it, almost equal in appearance. That visual equality carries scientific meaning. The outermost Oort Cloud lies near the limit where the Sun's authority must compete with the slow, collective influence of the Milky Way. The galaxy does not pull as a single nearby object. Its effect comes from the broad distribution of matter in the galactic disk and the larger galactic mass around the solar system. Over short periods, this influence is subtle. Over immense spans of time, it becomes decisive. The farthest icy bodies remain near the threshold, where a tiny change in speed or direction can alter whether they stay attached to the Sun or drift beyond secure return. This is one reason the region is described in theory rather than in certainty. It is not a sharply fenced province. It is a fading zone of weak attachment. Because of that weakness, the outer edge is not known with precision. Different estimates place it at different distances. No spacecraft has travelled through the full cloud. No telescope has imaged its structure directly. Astronomers infer its existence mainly from the paths of long-period comets and from dynamical models, meaning mathematical reconstructions of how gravity shapes motion across deep time. These methods indicate that a distant cloud is the best explanation for comets that enter the inner solar system from many directions. They also indicate that the cloud's farthest extent depends on how far the Sun's gravity can resist the steady, tidal influence of the galaxy. A tide in this sense is a gradual difference in gravitational pull across space, enough to stretch or redirect very distant orbits over millions of years. So the outermost Oort cloud is not only far away, it is fragile in definition. An icy body may still revolve around the Sun in a path lasting millions of years, yet that path can be slowly twisted by the galactic environment. The body remains part of the solar system, but not in the secure, orderly way of a planet. Its membership is provisional, held across such enormous scales that the outside world is always present. In this remote zone, interstellar space is not a destination waiting beyond a clean border. It is an influence already felt within the border itself. For that reason, the far edge of the Oort cloud can be understood as the Sun's last broad claim rather than its final wall. Here the solar system does not end in an object, a shock front, or a visible line. It fades. The outermost cloud marks a realm where home is maintained by the weakest thread of gravity, stretched almost to its limit by the wider galaxy. Nothing in this region appears busy, dramatic, or bright. It is quiet beyond description, yet within that quiet lies one revealing fact about the solar system. Its true size is measured also by how far the Sun can hold ancient icy fragments against the background pull of the Milky Way, and by how gently that hold gives way at the edge of the unseen. The outer Oort cloud is described not as a ring, not as a disk, and not as a belt, but as a broad spherical distribution surrounding the Sun on all sides. This shape matters because it separates the region from the more familiar architecture of the solar system. The planets move in paths that remain close to a common plane, like grains arranged in a very thin rotating sheet. Their regularity is one of the solar system's defining features. The outer Oort cloud belongs to a different order of structure. It is thought to extend above that plane, below it, and outward in every direction, forming a distant volume of icy bodies whose arrangement is almost the opposite of the flat planetary system near the Sun. This spherical character is not something astronomers have photographed. No telescope has looked outward and captured a luminous globe around the solar system. The region remains entirely inferred. Its presence is reconstructed from motion, from statistics, and from the rare occasions when one of its possible members leaves that darkness and begins the long fall toward the inner system. In this sense, The outer Oort cloud is one of astronomy's clearest examples of a structure known by consequence rather than by sight. It is accepted not because it has been seen directly, but because the behavior of certain comets is difficult to explain without a distant, nearly spherical source. The most important clue comes from long-period comets. These are comets that take more than 200 years to orbit the Sun, and many take vastly longer than that. When they appear in the inner solar system, they do not arrive only from the plane where the planets move. Their paths can come from almost any direction in the sky. Some descend from high above the planetary plane. Some rise from far below it. Some approach at steep angles that do not fit with a thin disk of origin. Over time, this broad spread of incoming directions has suggested that the reservoir feeding them must itself be roughly spherical. If the source were flat, the arrivals would show a flatter pattern instead. The sky distribution points toward a much more rounded and enclosing store of distant bodies. That insight becomes especially important because astronomy often learns about hidden populations through the motions of the small number of objects that escape them. In the middle of the 20th century, the Dutch astronomer Jan Oort studied the orbits of long-period comets and argued that they pointed to an enormous distant reservoir surrounding the solar system. The modern picture has grown more detailed since then, but the central logic remains familiar. A hidden population is inferred from the pattern of arrivals. The cloud bears his name because the broad shape of the evidence continues to support that early conclusion. That does not mean every orbit in the outer Oort cloud is random. Each body still travels under the Sun's gravity. Each follows a path that can be described in the language of celestial mechanics, the study of motion under gravity. But taken together, those paths appear to occupy a three-dimensional swarm rather than a two-dimensional sheet. The result is not a solid sphere filled uniformly with matter. It is a huge and sparse population whose members spend most of their existence separated by distances so large that the cloud remains invisible as a collective object. The spherical picture is therefore a matter of orbital distribution, not of surface appearance. Its invisibility follows naturally from both distance and scale. Even a large icy body at such a distance reflects almost no sunlight toward Earth. Smaller bodies vanish completely into darkness. The cloud also lacks dense gas and dust that might scatter light into a visible glow. The outer Oort cloud is therefore not hidden in the sense of being obscured behind a curtain. It is hidden because it is too thin, too dark, and too remote to announce itself. The human eye would see nothing of it. Present telescopes also see nothing of it directly. The region lives in theory, and the theory rests on repeated patterns in observed comet trajectories. Because the region is inferred rather than imaged, its exact shape remains approximate. Astronomers speak of a roughly spherical cloud, not a perfect one. The outer population may be stretched, lopsided, or uneven in detail. It may contain clumps caused by ancient gravitational disturbance. It may also blend gradually into less populated space without a sharp outer skin. Even so, the overall concept remains stable. The distant source of many long-period comets appears much more spherical than the inner planetary system. That contrast is one of the strongest signs that the cloud preserves a record of processes unlike those that govern the major planets today. The very idea of a sphere around the Sun also changes the sense of direction in the solar system. Near the planets, inward and outward usually dominate thought. In the outer Oort cloud, above and below become equally meaningful. There is no privileged horizontal surface. The Sun sits near the center of a volume that surrounds it on all sides. and any member of the cloud may spend nearly all of its long existence in a direction that has little relationship to the plane of Earth, Jupiter, or Neptune. The planetary system, which seems so expansive when viewed from Earth, becomes only a very small inner flattening inside a much larger and far more diffuse enclosure. The outer Oort cloud is therefore unseen not because it is doubtful in the casual sense, but because it belongs to a scale where direct observation remains beyond present reach. Its strength as a scientific idea comes from coherence. The model explains why certain comets arrive as they do. It explains why their directions are so widely distributed. It explains why the solar system may possess a distant spherical reservoir, even though its inner regions are flat. Observations indicate that such a reservoir is the best current explanation. It remains uncertain in its detailed boundaries, in its total population, and in the exact degree of its roundness. Yet the broad picture endures. Around the Sun, far beyond the visible worlds, there appears to be an unseen spherical expanse, known only through the motions of a few returning messengers from the dark. The outer Oort cloud is often imagined as crowded because the word cloud suggests fullness. In ordinary life, a cloud has texture, shape, and visible density. It gathers light and announces its presence. The outer Oort cloud does none of these things, even if it contains an enormous number of icy bodies. The distances between them are so great that the region remains, in practical terms, almost entirely empty. This is one of its most important features. Its mystery does not come from abundance alone. It comes from abundance spread across such a vast volume that emptiness becomes the dominant condition. Astronomers think the cloud may contain billions or even trillions of icy objects. That sounds like a crowded population until the scale of the region is considered. The outer cloud surrounds the Sun across a spherical expanse, reaching through tens of thousands of astronomical units and perhaps much farther. When a very large number of small bodies is distributed through such an immense volume, the result is not congestion but isolation. Each object spends its long existence in darkness with almost no nearby company. The nearest neighbour may still be unimaginably far away. In that setting, the idea of a region must be understood statistically rather than visually. The cloud exists as a population, not as a packed scene. This sparse arrangement shapes every physical experience that could occur there. A body drifting in the outer Oort cloud does not pass through swarms of debris. It does not move through a glowing field of dust. It does not travel beside a procession of companion worlds. Most of the time, nothing changes in its surroundings at all. There is no horizon marked by nearby objects, no repeated crossing of familiar lanes, no sign of the busy orbital architecture known from the planetary system. The sky would not display a surrounding shell of frozen bodies. It would show stars, darkness, and one distant sun. Even that sun would no longer dominate the sky by brightness in the way it does from Earth. It would remain much brighter than ordinary stars, but it would not flood the landscape with daylight. At the outer edge of the cloud, sunlight is so reduced that the environment remains locked in deep, cold, and weak illumination. Surfaces may still reflect light, but only faintly. The region does not glow because there is too little material and too little incoming light. This is why the cloud has never been seen directly. Its members are individually too dim and together too diffuse to make a visible structure. The emptiness also means that collisions between Oort cloud bodies are expected to be rare. Over immense spans of time, impacts can happen, but the region is not a place of constant smashing and grinding. In denser parts of the early solar system, collisions help build planets and reshape small bodies. In the outer Oort cloud, the average separation is so large that most objects simply remain apart. Their history is defined less by frequent contact and more by long endurance. They preserve ancient material not because nothing ever affects them, but because so little happens quickly. That stillness gives the outer cloud a special scientific importance. It may contain some of the oldest surviving fragments from the solar system's early formation, stored in a region where change is slow and encounters are infrequent. Yet even here, the emptiness must be described carefully. The cloud is not a museum cabinet with each object neatly suspended and unchanged forever. Tiny impacts from dust, exposure to cosmic radiation, and the steady passage of time can still alter surfaces, but these changes happen against a background of extreme separation. The defining fact remains that each icy body lives alone for long intervals beyond easy human intuition. This is also why words such as swarm or shell can mislead unless they are handled with care. A swarm in familiar experience contains restless nearness. A shell suggests a layer one might cross. The outer Oort cloud is neither in any ordinary sense. A spacecraft passing through part of it might travel for a tremendous distance and encounter nothing at all. It could remain inside the cloud's proposed volume while observing only empty space around it. Membership in the region would not guarantee any visible sign of being there. The cloud is a structure of orbits and probabilities, not a visible medium. In this way, the outer Oort cloud resembles the wider universe more than the inner solar system. Galaxies themselves are full of stars, yet the distances between stars are so large that a galaxy is mostly empty. The same principle holds here at a smaller scale. A vast collection of bodies does not create fullness unless they are also close together. The Oort cloud contains matter, but matter diluted across a huge sphere. Emptiness is therefore not the absence of the cloud. Emptiness is the cloud's natural form. This diluted population also helps explain why long-period comets can remain stored for such long times before anything disturbs them strongly enough to send them inward. In a dense environment, repeated encounters would rapidly reshape or remove orbits. In the outer cloud, long quiet intervals are normal. Bodies can remain distant and hidden because space itself protects their separation. Their isolation is not an accident. It is the direct outcome of the cloud's enormous size and loose population. So the darkness between icy bodies is not a minor detail. It is the central texture of the outer Oort cloud. Everything there is defined by spread, silence, and distance. The region may contain a huge reserve of frozen remnants, but it is not filled in the way the mind first imagines. It is a realm where matter is present without crowding, where structure exists without visibility, and where the solar system extends outward not as a bright boundary or a dense field, but as a near-empty sphere of ancient objects suspended in long separation around a distant sun. In the far outer Oort cloud, motion continues without urgency. Nothing there stands still, yet almost nothing seems to move. The bodies of this distant region remain under the sun's gravity, but they travel so far from the centre and along such enormous paths that their progress becomes difficult to imagine in ordinary terms. Near the sun, motion is easy to notice. Planets complete their circuits in years or in decades. In the outer Oort cloud, orbital time stretches so far that motion becomes a matter of deep time rather than observation. A single circuit around the sun can last hundreds of thousands, millions, or in some cases tens of millions of years. These paths are usually described as very large ellipses. An ellipse is an oval path with the sun located away from the centre rather than exactly in the middle. The closer an object comes to a circle, the more even its distance remains as it moves. The more stretched the ellipse becomes, the more strongly its distance changes between its nearer and farther parts. In the outer Oort cloud, many objects are thought to occupy extremely stretched paths. For most of their orbit, they remain very far from the Sun, moving slowly through the cold darkness of the outer reaches. Only a small part of such a path lies relatively less far from the Sun. The rest is spent in remote distance where the Sun's pull still governs, but does so gently. This slow motion follows a simple rule of gravity. The farther an object is from the Sun, the weaker the Sun pulls on it, and the slower the object needs to move in order to remain bound. In the inner solar system, planets travel quickly because the Sun's grip is strong. In the outer Oort cloud, that grip is faint, and the pace of orbital motion becomes correspondingly small. Speed is not absent, but on these scales it produces almost no visible change from one human generation to the next. An object may continue faithfully along its orbit while shifting so little in position that the movement would feel nearly frozen. The farthest part of an orbit is also the slowest. When a body reaches the most distant portion of its path, it lingers there. Gravity has weakened it to a drift, and time seems to pool around that slow turn. This does not mean the object stops. It means that most of its orbital life is spent in the remoteness of the outer arc, where change happens with extraordinary patience. By contrast, when an orbiting body later passes through a less distant part of its ellipse, it moves more rapidly. This uneven rhythm belongs to all elliptical motion around the Sun, but in the outer Oort cloud the contrast becomes extreme because the orbits themselves are so immense. That unevenness shapes the character of the region. The outer cloud is not simply a store of distant bodies placed at fixed radii like beads on a spherical surface. It is a moving population, but one whose movement is concentrated into vast, slow loops. At any given time, many members of the cloud are likely near the outer stretches of their paths, simply because that is where they spend the greatest share of their orbital lives. The result is a region whose stillness is real only in appearance. It is built from motion, but motion drawn out to such length that the cloud seems almost suspended. This is one reason the outer Oort cloud remains beyond direct experience. Human intuition forms around quick change, repeated cycles, and visible return. The motions here deny all three. No observer could watch one of these bodies complete its circuit within a lifetime, or within the span of civilizations. Even the idea of an orbit becomes abstract. It must be understood mathematically rather than watched. Astronomy often studies motion from repeated measurements gathered over time, but in this region the full pattern is far too long to witness directly. Knowledge comes instead from the laws of gravity, from the shapes of cometary paths seen closer to the Sun, and from models that reconstruct how distant objects may travel over immense ages. The weakness of the Sun's hold in the outer cloud also gives these motions a delicate quality. The bodies remain gravitationally bound, meaning they still belong to the solar system, but they do so loosely. Their orbital energy sits near the threshold between secure return and release. A modest change in such a distant orbit can matter greatly, because the original binding is already so weak. Yet as long as the path remains bound, the object continues its immense circuit, tracing a route so broad that the solar system reveals its size not through brightness or mass, but through duration. The length of the orbit becomes a measure of the reach of the Sun. The geometry of these paths also helps explain why the Oort cloud is treated as a volume rather than a layer. If the orbits point in many directions and rise to many inclinations, Then the moving bodies fill a sphere-like region over time. Inclination means the tilt of an orbit compared with the common plane of the planets. In the outer cloud, those tilts are thought to span a wide range. Some orbits may lie at steep angles. Over long spans, this varied set of slow trajectories helps create the broad spherical character inferred from the arrival directions of long-period comets. Still, the motion is not chaotic in the simple sense of disorder. Each body follows a lawful path shaped by gravity. The apparent strangeness comes from scale, not from a breakdown of the rules. The same principles that guide Earth around the Sun also guide a distant icy body through the outer Oort Cloud. The difference lies in magnitude. The path is far larger, the pace far slower, and the timescale so extended that what is dynamic in theory becomes almost motionless in appearance. So the outer Oort Cloud lives in a state of extreme slowness. Its members circle the Sun on paths that can exceed the rise and fall of species, climates, and continents. Their motion is real, continuous, and obedient to gravity, yet stretched across such vast distances that the region seems suspended between orbit and stillness. In this distant sphere, the solar system does not end in fixed silence. It persists in almost invisible motion, with ancient icy bodies tracing enormous curves around a sun that remains their centre only by the gentlest of pulls. At the outer rim of the Oort Cloud, the Sun is no longer the only large influence shaping motion across long ages. The bodies there still belong to the solar system, yet they do not move in isolation from the rest of the Milky Way. The galaxy surrounds the Sun not as a nearby object with a single obvious pull, but as a vast distribution of stars, gas, dust, and dark matter whose combined gravity acts slowly across space, in the outermost cloud where the Sun's grip is already weak. That larger galactic environment begins to matter in a quiet but persistent way. Its effect is often described as a galactic tide, meaning a gradual difference in gravitational pull from one part of the region to another. A tide in this sense does not resemble an ocean wave. It is not a crest moving through space. It is a stretching influence. When gravity acts slightly more strongly on one side of an extended region than on the other, paths can be altered over time. Near the planets, the Sun's control is strong enough that this outside influence matters little. At the far rim of the Oort Cloud, the balance changes. The Sun still holds distant icy bodies in orbit, but the galaxy can slowly reshape the details of those orbits. It does not need to overpower the Sun in a single moment. It works through persistence, not forceful interruption. The solar system moves within the Milky Way as it travels around the galactic center. It is embedded in the broad gravitational field of the galactic disk and the matter around it. Because the Oort Cloud extends so far from the Sun, its outermost members occupy a large enough volume that this background field is not the same everywhere across the cloud. That small difference is enough to matter over millions of years. The outer cloud is therefore not only a solar structure, it is also a place where the solar system and the galaxy meet in a practical dynamical sense, with local gravity and galactic gravity acting together on the same remote objects. This slow galactic shaping affects orientation as much as speed. A distant icy body may keep circling the Sun, yet the direction and form of its orbit can be gently bent. Its farthest point may shift, its tilt may slowly change, its path may become more stretched or less stretched depending on the details of its motion and its position within the larger field. These changes are subtle when measured against a single lifetime, but across deep time they accumulate. the far rim of the cloud becomes a place where long stability does not mean complete permanence. Orbits survive, yet they do not remain perfectly fixed. This helps explain why the Oort cloud is understood as a dynamic reservoir rather than a frozen arrangement. The word reservoir suggests stored material, and that is true in a broad sense. But the bodies in the outer rim are not simply parked forever in unchanged positions. They are part of a distant population whose paths are continually adjusted by the surrounding galaxy. The adjustments are usually small, but in such a weakly bound region, small changes are important. When the Sun's hold is already stretched close to its limit, even gentle outside influence can alter the long-term fate of an orbit. The galactic tide also helps preserve the cloud's broad, spherical character. If the distant reservoir were shaped only by the flat planetary system from which its bodies once came, it might retain more of that flattened origin. Instead, the outer Oort cloud is thought to become rounded because long exposure to weak, outside gravitational effects helps scatter orbital directions more widely. Over immense spans, the galaxy acts like a slow hand smoothing out memory of the inner plane. The result is not perfect uniformity, but a greater degree of spherical spread than one would expect from the solar system's flat interior alone. At the same time, this influence makes the outer boundary uncertain. The farther from the Sun an object drifts, the more vulnerable it becomes to the galactic field. There is no precise distance at which solar ownership ends and galactic control begins. The transition is gradual. A body may remain bound on one orbit and be lost on another. The outer rim is therefore best understood as a threshold rather than a line. It marks the part of the solar system where belonging becomes weak enough that the background structure of the Milky Way can steadily rewrite the geometry of distant motion. This region reveals something important about scale. The solar system is often imagined as a self-contained system, defined only by the Sun and its own members. That image works well in the inner regions, where the Sun dominates so strongly that outside forces are minor. At the far rim of the Oort cloud, the solar system is no longer self-contained in that simple way. It remains a real gravitational family, but it exists inside a larger galactic setting that leaves marks on its outermost members. The rim is therefore both local and cosmic. It belongs to the Sun, yet it carries the signature of the galaxy. Even the quietness of the region takes on new meaning under this view. The far outer cloud appears still and isolated, but its long history is shaped by a continual exterior pressure too weak to see and too slow to feel directly. What seems empty is nonetheless connected to the mass of the Milky Way. What seems motionless is gradually being retuned by a field that acts across enormous distances. Observations indicate that this galactic influence is essential for understanding how the outer Oort cloud behaves over time. It remains uncertain in detail how individual orbits respond over the full life of the solar system, but the broader conclusion is clear. The remote rim is not shaped by the Sun alone, so the galactic tide is one of the defining conditions of the outermost Oort cloud. It does not break the solar system open in a dramatic instant. It does not produce a visible edge or a violent border. Instead, it works with immense patience, subtly stretching and redirecting the weakest solar orbits at the farthest distances. In that distant region, the Sun's last claim is maintained under constant pressure from the wider Milky Way, and the unseen cloud remains suspended between two scales of gravity, local enough to orbit the Sun, yet distant enough to feel the steady shaping hand of the galaxy. The outer Oort cloud does not spend its history under the Sun and the galaxy alone. From time to time, other stars pass through the wider neighborhood of the solar system, and although none need come especially close to the planets to matter, their gravity can still reach into the farthest cloud, in the outermost regions, where the sun's hold is already weak and the galactic tide is always at work. A passing star becomes another quiet source of disturbance. It does not need to strike, brush, or enter the cloud in any dramatic way. Its effect can begin at a great distance. Across long spans of time, a single passage can slightly reshape many remote orbits, while repeated passages over the age of the solar system help make the cloud an unsettled reservoir rather than a perfectly preserved shell. A stellar passage is best understood as a moving gravitational encounter. Every star carries mass, and mass bends motion. When another star travels through the Sun's broader galactic neighborhood, its gravity does not act like a sharp blow. It acts more like a temporary leaning on the distant architecture of the cloud. The nearer and more massive the passing star, the stronger the effect can be. But even a modest star can matter if it passes close enough, and if the icy bodies it influences are already only loosely tied to the Sun. In the outer Oort Cloud, looseness is the essential condition. A faint change can be enough to alter a path that is already delicately balanced. These encounters are rare on human timescales, but the solar system has existed for billions of years, and over such duration rarity becomes normal. The Sun travels through the Milky Way among other stars, not through empty isolation. Most stars remain far away. Yet distances between stars, though enormous, are still small enough on galactic scales that occasional close passages are expected over deep time. Each passage brings a new pattern of gravitational influence depending on the star's mass, speed, direction, and minimum distance from the Sun. The outer Oort Cloud records these encounters not as visible scars but as slow changes in orbital shape and direction. This is one reason the outer cloud cannot be treated as a static archive. It may preserve ancient material, but it does not preserve ancient arrangements exactly. A passing star can tip or stretch distant orbits. It can loosen some and tighten others. It can increase the chance that a body will remain in the remote cloud, or it can make that body more vulnerable to drifting away from the Sun entirely. Because the outermost members are so weakly bound, a change that would be negligible near the planets can have lasting importance here. The farther the orbit, the more easily it can be rewritten. The effect of a stellar passage depends strongly on geometry. If a star moves in one direction relative to the Sun, it may pull more strongly on one side of the cloud than another. Bodies already positioned along that side can feel a greater change. Those elsewhere may feel much less. The result is not usually a uniform disturbance spread smoothly across the entire sphere. It is often selective, acting more strongly in some regions and on some orbits than on others. Over time, many such unequal encounters can help make the outer cloud uneven in detail, even if its broad overall form remains roughly spherical. This selective nature also helps explain why the cloud structure remains uncertain. Astronomers can model the average effects of passing stars, but the exact history of every close encounter is difficult to reconstruct across billions of years. Some past stars can be traced in principle if their motions are known well enough, yet much of the ancient record is lost in the complexity of galactic motion. Observations indicate that stellar passages play an important role in shaping the distant cloud. It remains uncertain exactly which encounters matter most across the full history of the solar system and how much each one contributes to the present arrangement. The uncertainty is not a flaw in the basic picture. It belongs naturally to a structure formed and modified over such long times and such huge distances. A nearby stellar passage can also work together with the galactic tide rather than acting alone. The tide provides a steady background shaping. A passing star adds a temporary extra disturbance. In the inner solar system, the planets remain strongly governed by the Sun and scarcely notice such events in any direct way. In the far outer cloud, the combination can be significant. A body already near the threshold of secure solar attachment may have its orbit shifted enough that its future changes completely. It may remain in the cloud but on a new path. It may become more likely to drift inward later. It may even be removed from the Sun's possession and released into interstellar space. That last possibility gives passing stars a quiet power. They do not merely stir the cloud, they can erode it. Over billions of years, some fraction of the original distant population is likely lost because stellar encounters and galactic tides gradually free the weakest members. The Oort Cloud, if it formed early and large, is therefore not necessarily the same in size or population today as it was long ago. It is a surviving remnant, not an untouched beginning. At the same time, the same disturbances that remove some bodies may help preserve the cloud's role as a long-lasting reservoir by continually redistributing orbits rather than allowing the outer structure to collapse into a simpler pattern. There is also a larger historical possibility. The early Sun is thought to form in a stellar nursery, meaning a birthplace among many nearby stars. If so, the young solar system may have experienced closer and more frequent stellar passages in its earliest age than it does now. That crowded beginning could have helped shape the distant cloud from the start. Yet in the present outer region, the important fact is simpler. The solar system does not carry its farthest icy bodies through the galaxy without interference. Other stars pass, their gravity reaches in. The cloud remembers. So the outer Oort Cloud lives under a kind of slow weather, made not of wind or light, but of gravity from wandering stars. Most of the time the region remains dark, sparse, and almost still. Yet over immense ages, passing stars introduce moments of deep disturbance. They bend the weakest orbits, alter the balance of solar attachment, and help ensure that the farthest cloud is never perfectly settled. In that remote sphere, even the silence is not permanent. It is only the long interval between encounters. The outer Oort Cloud is not only a place of storage, it is also the place where some of the solar system's longest journeys begin. A distant icy body may spend millions of years in slow orbit under the weakest hold of the Sun, shaped gently by the galactic tide and by the passing influence of stars, until at last its path changes just enough to send it inward. The change does not need to be violent. In fact, it is usually small. What matters is not the size of the disturbance alone, but the fragility of the original orbit. In the outer shell, where solar binding is already slight, a subtle shift can transform a remote and lingering circuit into the beginning of a deep inward descent. This release is best understood as a change in orbit rather than an escape from the cloud in the ordinary sense. The object does not break free of the Sun, it remains attached, but on a new path. Its orbit becomes more strongly elongated, meaning the difference between its farthest and nearest distances from the Sun grows greater. At first, the body may still spend most of its time in the remote outer cloud. It does not suddenly rush inward in a continuous dramatic fall. It begins instead to follow a new ellipse whose distant end remains far out in darkness, while the nearer end has been drawn significantly closer toward the Sun than before. That shift marks the start of its transformation from a silent outer member of the cloud into a future long-period comet, A comet in this context is not defined first by its bright tail. It begins as an icy body whose orbit takes it from the deep cold of the solar system toward warmer regions. The tail appears only later, when sunlight becomes strong enough to heat surface ice and release gas and dust. In the outer Oort cloud, none of that is yet visible. The object remains dark, frozen, and far away. What has changed is orbital geometry. A body that once kept almost all of its path in the cloud now acquires a route that reaches inward across great distances. The release happens in mathematics first, in the shape of the orbit, long before it becomes a spectacle. The agents of release are the same quiet forces that shape the outer rim more generally. The galactic tide can slowly lift or lower part of an orbit relative to the planetary plane, and in doing so it can alter how close that orbit later comes to the Sun. A passing star can add a temporary pull that nudges the path into a more extreme form. Sometimes the combined effect is enough to reduce the object's perihelion, the point of closest approach to the Sun. Once that nearest point moves inward, the future of the body changes. It is no longer confined to the remote shell alone. It begins a journey that crosses larger parts of the solar system, though it may still take a very long time before the inward leg is complete. The release is therefore both gradual and decisive. Gradual, because the forces involved often work over long stretches of time, and because the object may still need a great span to move along its altered orbit. Decisive, because once the orbit is shifted far enough, the body has entered a different dynamical class. Dynamical in this sense refers to how gravity organizes motion. The released object still belongs to the distant reservoir in origin, but its future is now linked to inward travel. It has moved from quiet storage into transit. This transition reveals something subtle about the outer shell. It is not simply the place where long-period comets come from. It is the place where the probability of release is always present. Most bodies remain far out for immense times. Only a small fraction are disturbed strongly enough to begin the inward route. Yet given the enormous population of the cloud and the vast duration of the solar system's history, even a low release rate is enough to supply occasional newcomers. The cloud does not empty quickly because it is so large, and because most objects remain undisturbed for long intervals. It yields only a small number at a time, with each release emerging from very slow gravitational preparation. There is also an important asymmetry in this process. To move a distant object inward, the disturbing influence does not need to push it directly toward the Sun as though throwing a stone. It only needs to change the orbit enough that solar gravity does the rest. Once the ellipse is altered, the body naturally follows the new path. In that sense, the outer cloud releases comets not by expelling them away, but by reshaping how they remain bound. The Sun still governs the motion. The external influences only revise the terms of that governance. Because the original orbits in the outer Oort cloud are so large, the early phase of release is still dominated by silence and cold. The object may have been set on an inward-reaching path, yet for a long time it remains visually indistinguishable from the other frozen bodies around it. No tail appears, no glow surrounds it, no sudden change announces its altered destiny. It continues through deep darkness, carrying within its orbit the only sign that it has become something different. The transformation is therefore hidden twice over, first because the region itself is unseen, and again because release begins as an invisible change in trajectory. This invisibility is one reason the Oort cloud remains a theoretical source rather than an observed nursery. Astronomers do not watch these objects being nudged inward one by one at the far edge. They infer the process from the orbits of long-period comets after those objects have travelled much farther along their paths. The reasoning is strong because the pattern fits gravitational theory, and because the cloud provides a natural reservoir for such bodies. Observations indicate that many long-period comets are best explained as former outer cloud objects whose orbits have been disturbed inward. It remains uncertain which particular past disturbances release any one comet, or how often each mechanism dominates in detail. The broader process, however, is well supported. So the outer shell is not merely an invisible boundary of frozen remnants, it is also a threshold of activation. Here a body can pass from remote endurance into slow migration without changing its substance, without brightening, and without any dramatic local event. The beginning of a comet's inward career is therefore one of the quietest transitions in the solar system. It starts in the darkness of the outer Oort Cloud, where a slight gravitational change turns a nearly forgotten icy fragment into a traveller on one of the longest possible roads toward the Sun. Between the loose outer shell and the deeper inner reservoir lies no sharp dividing wall. The Oort Cloud is often spoken of as though it consists of two clear parts, outer and inner, but the region between them is better understood as a long transition through distance, binding strength, and orbital character. This middle expanse does not announce where one domain ends and the next begins. Instead, it marks a gradual change in how securely icy bodies belong to the Sun, and in how strongly outside influences can alter their paths. It is a zone of passage, not in the sense of rapid movement, but in the sense of slow dynamical change spread across enormous space. Here the Sun's gravity still acts weakly compared with the inner solar system, yet it has become more reliable than at the farthest rim. Bodies in these middle distances remain distant beyond ordinary imagination, but they are not balanced quite so close to loss. The galactic tide still matters. Passing stars can still disturb orbits. Even so, the grip of the Sun becomes somewhat firmer than it is in the outermost shell. This does not produce a dramatic new appearance. The region remains dark, sparse, and unseen. What changes is the degree of attachment. An object here is generally less vulnerable to removal and more likely to remain part of the solar system across long spans. That increased attachment shows itself through orbital behavior. In the outermost cloud, a modest disturbance can have large consequences because the original bond is so weak. In the middle distances, orbits are still immense, but the same kind of disturbance may produce a smaller proportional change. The body remains on a very long path around the Sun, yet the terms of that orbit are less fragile. The result is a region where the solar system holds its distant matter with more confidence, though still with extraordinary slowness and at extraordinary scale. It is not a secure inner system, but neither is it the fading edge of solar authority. This transition is important because it helps explain how the Oort Cloud can function as a lasting structure rather than a cloud that simply dissolves at its outer rim. If all its members were bound only as weakly as those at the farthest edge, then the wider galaxy and repeated stellar passages would strip the cloud too effectively. The middle distances provide a deeper layer of endurance. Bodies here are still remote enough to preserve the broad character of the Oort Cloud, yet they are held strongly enough that the reservoir can persist over billions of years. The cloud's survival depends not only on its outer shell, but on this gradual inward strengthening. Even so, the middle region remains part of the same vast emptiness. The bodies here are still separated by great intervals. A traveller crossing this domain would not see a crowd gathering toward the centre. There would be no visible thickening in the ordinary sense, no boundary line passed, no clear moment of entry into a new province. Distance remains the ruling condition. The Sun still appears as a star, brighter than the rest, but nowhere near the overwhelming brilliance known from the planetary system. Darkness still governs the environment, and the population still exists mainly as an inferred swarm of remote, icy bodies following immense paths in many directions. The transition, therefore, belongs more to physics than to appearance. It is a change in orbital resilience, in the balance between solar control and outside disturbance, and in the long-term stability of membership. In these middle distances, a body is still shaped over time by the galaxy, yet the galaxy no longer presses upon it with the same relative power it has at the far rim. The Sun regains some authority, not by becoming strong in an absolute sense, but by becoming less weak relative to competing influences. That distinction matters. Nothing in this region is close, bright, or fast. The change is entirely one of gravitational balance. Because the region is transitional, its exact extent is uncertain. Different models place the shift between outer and inner cloud at different distances. The difficulty comes partly from the fact that the cloud itself is not directly observed, and partly from the fact that its structure is statistical. No line can be drawn through a picture because no picture exists. Instead, astronomers infer these layers from dynamical reasoning, meaning they ask how objects at different distances are expected to behave under the combined effects of the Sun, the galaxy, and passing stars. The answers suggest a continuum rather than a clean break. The middle distances are where that continuum becomes most evident. This part of the cloud also reveals how misleading simple diagrams can be. A sketch may show nested shells, perhaps one outer sphere and one inner sphere, arranged neatly around the Sun. Such drawings are useful as broad guides, but the real structure is unlikely to be so orderly. The middle region is probably mixed, with orbits of many shapes and degrees of vulnerability overlapping through a large volume. Some objects may behave more like members of the outer shell. Others may behave more like part of the deeper reservoir. What defines the region is not uniformity, but gradual change from one general regime to another. That gradual change also affects how comets may later be supplied to the inner solar system. The outer shell is especially exposed to external nudging, but the middle distances help connect that weakly held exterior to more persistent populations farther in. They form a broad bridge of long-period motion, where a body may remain stored for immense ages while still belonging to a cloud whose outer regions are continually shaped by the galaxy. The Oort Cloud is therefore not best imagined as two separate objects. It is one distant system with a changing internal character, and the middle distances are where that change becomes visible in theory. In this sense, the region between outer and inner is a slow corridor of gathering attachment. The farther outer shell remains the Sun's most fragile claim. Deeper within, the Sun's hold becomes more dependable, though never forceful in the way it is among the planets. The middle distances carry the cloud inward without spectacle, preserving its darkness, silence, and immense separations while gradually shifting the balance of power toward longer stability. Nothing in this region shines to mark the transition. Nothing breaks the stillness. Yet across these enormous spans, the Oort Cloud passes from the weakest edge of solar, belonging toward a deeper and more enduring store of distant icy matter. Deeper within the Oort Cloud, the Sun's distant hold becomes stronger without ever becoming strong in the familiar sense of the planetary system. This inner region is often called the Hills Cloud, after the astronomer Jack Hills, who argued that a denser inner reservoir may exist inside the broader Oort structure. It is not a place of bright discovery or direct observation. Like the rest of the Oort Cloud, it remains unseen. Yet in theoretical models it plays an important role because it offers a more securely bound population of distant icy bodies, held far beyond the known planets but less vulnerable than the objects of the outer shell. The word inner can be misleading here. It does not refer to nearness in any ordinary way. The Hills cloud, if it exists in the form many models suggest, still lies at immense distances from the Sun, far beyond the region where the major planets travel and far beyond Pluto. Even its nearer estimates remain within a realm of deep cold, extreme separation, and very long orbital periods. Nothing about it resembles the crowded architecture of the planetary zone. It remains part of the deep outer solar system, silent and dark. What makes it inner is only relation. It lies inward of the loose outer shell and occupies a region where solar binding becomes more dependable. This stronger attachment is the defining feature of the Hills cloud. Its members are thought to orbit the Sun on paths that are still enormous, but less easily unbound by passing stars or by the slow tidal influence of the Milky Way. The galaxy still matters here, yet the Sun's grip has strengthened enough that distant bodies can remain stored with greater long-term stability. In this sense, the Hills cloud is often understood as a deep reserve, a hidden interior stock from which the broader Oort population can be sustained over billions of years. The idea of a reservoir is especially useful in explaining endurance. The outer shell is fragile. Its bodies are weakly held and more exposed to loss. If the Oort cloud consisted only of that outermost population, then the combined effects of galactic tides and stellar passages might gradually erode it too efficiently. The Hills cloud provides a more persistent source. It may continually contribute bodies outward or supply the long-period comet population through slow, dynamical reshaping, while itself remaining more durable than the remote edge. In that way, the inner reservoir is not separate from the outer cloud in purpose. It is part of the same distant system, but it serves as its deeper storehouse. Models often suggest that this region could contain a substantial fraction of all Oort cloud bodies, perhaps even more than the outer shell. The exact proportion remains uncertain because the cloud has never been observed directly, and because the orbital behavior of such distant objects must be reconstructed from theory. Still, the concept is compelling, because it helps explain how a distant comet reservoir might survive across the age of the solar system. A denser inner concentration, more tightly bound to the Sun, offers a natural form of long-term memory. It allows the cloud to lose bodies at its edges without disappearing as a whole. Denser, however, must be understood carefully. The Hills cloud is not dense by everyday standards. It is dense only relative to the outer shell. The separations between bodies are still enormous. Empty space still dominates the environment. A spacecraft moving through this inner reservoir might still travel for vast distances without approaching any object closely. The region remains more a population than a scene, more an inferred structure than a visible realm. Yet compared with the broad outer cloud, the inner reservoir may hold more objects per unit volume, and may therefore represent a deeper concentration of the solar system's distant icy remnants. Its orbital character reflects that greater concentration and stronger solar control. Paths in the hills. Cloud are still long and highly stretched, but the bodies are more securely attached to the Sun than those at the outer edge. Disturbances that might remove a very distant object altogether may only modify an inner cloud orbit. This makes the Hills cloud dynamically important. Dynamical here means important in the way motion changes over time under gravity. The region may act as a stabilizing interior reserve, one whose members can be perturbed, shifted, and occasionally sent farther outward or inward while the reservoir itself remains in place across deep time. Even so, uncertainty remains central. Observations indicate that some form of inner reservoir is plausible and perhaps likely, but its size, shape, population, and exact boundaries remain uncertain. It may not form a neat sphere. It may merge gradually into the outer cloud above and into other distant small body populations below. Different simulations produce different balances between inner and outer members, depending on assumptions about the solar system's early history and its later galactic environment. The Hills cloud is therefore not a completed map. It is a strong theoretical component of the broader Oort picture, supported by dynamical logic more than by direct evidence. That logic rests on persistence. A lasting comet reservoir seems easier to maintain if there is a deeper, better protected store of bodies inside the more vulnerable outer shell. In that picture, the Hills cloud becomes the quiet heart of the Oort system, not bright, not crowded, not directly seen, but essential. It sits in the deep outer darkness where the sun still rules weakly, yet with enough authority to preserve a hidden reserve through immense stretches of time. Around it, the wider cloud remains open to slow loss and reshaping. Within it, the solar system appears to keep a more durable memory of its distant scattered remnants. So the inner Oort cloud is best understood as a concealed reservoir of stronger belonging. It remains remote almost beyond language, yet relative to the outer shell, it is a deeper centre of stability. Its members are still icy wanderers on immense paths, but they are held with greater firmness and gathered, at least in theory, into a more concentrated store. In that unseen interior, the Oort cloud ceases to be only the fading edge of the sun's gravity and becomes instead a layered outer domain, with a hidden reservoir preserving the solar system's distant population in long, cold silence. Within the deeper reservoir of the inner Oort cloud, the most important scientific question is not only where the bodies are, but what they are. These remote objects are thought to be ancient small worlds made largely of ice mixed with rock and dust, preserved in the deep cold far beyond the known planets. They are often described as planetesimals, a word for the small building blocks from which planets begin to form in the early solar system. In this distant setting, the term does not imply that they are on their way to becoming planets now. It means that they are remnants from that early age, material left over from the same broad process that once built the major bodies closer to the Sun. The dominant picture is that Oort cloud bodies contain large amounts of frozen volatile material. Volatile in planetary science means a substance that can easily turn to gas when warmed. Water ice is important, but it is not thought to be the only ice present. Carbon dioxide, carbon monoxide, methane, ammonia, and other frozen compounds are also expected in varying amounts. These materials are familiar in studies of comets, because when a long-period comet approaches the Sun, heat can drive such ices from solid into gas, releasing dust and producing the coma and tail. A coma is the temporary atmosphere of gas and dust that surrounds an active comet near the Sun. In the inner Oort cloud itself, however, there is almost no such activity. The cold keeps these substances locked in place. Mixed with the ices is rocky material, meaning silicate minerals and other non-volatile matter that does not easily evaporate under solar heating. Dust is part of this rocky component, though the word dust in space can be misleading because it covers a wide range of grain sizes, from very fine particles to larger fragments. The distant bodies of the inner Oort cloud are therefore not expected to be made of pure clean ice, like clear frozen water on Earth. They're better imagined as dirty, icy relics, mixtures of frozen compounds and mineral material assembled in the early solar system and later scattered outward into permanent cold storage. Their exact proportions likely vary from one object to another. Some may be richer in water ice. Some may contain more carbon-rich compounds. Some may be denser and more rock-heavy if they form closer to the Sun before scattering outward, while others may preserve more volatile material if their origins lie farther from the early Sun. Observations of comets that return inward provide clues to this diversity. When those comets become active, the gases and dust they release offer indirect evidence about their composition, yet such evidence is incomplete because activity can alter what is seen, and because the bodies observed near the Sun may not represent the full range of material stored in the distant cloud. The inner reservoir itself remains unvisited and unseen. The cold of the inner Oort cloud is central to this composition. Far from the Sun, temperatures remain so low that volatile compounds can survive for immense spans without the repeated heating and loss that affect smaller bodies moving closer in. This is why the Oort cloud is so valuable scientifically. It may preserve matter from the early solar system in a relatively unprocessed state. Unprocessed in this context does not mean perfectly unchanged. It means less altered by repeated warming, melting, and chemical cycling than material that spends long periods near the Sun. The cloud's bodies are not untouched, but they are protected from many of the active transformations that shape planets and inner comets. This preservation likely includes organic compounds as well. Organic in planetary science refers to carbon-based molecules, not to life. Many small icy bodies in the outer solar system appear to contain complex carbon-rich material. Such compounds can darken surfaces and help explain why comet nuclei, the solid central bodies of comets, often appear very dark rather than bright white. The same may be true of many bodies stored in the inner Oort cloud. Though they contain ice, their surfaces may be coated with dark material formed through long exposure to radiation or inherited from early chemical processes in the solar nebula, the disk of gas and dust from which the solar system forms. The word nucleus is useful here because many long-period comets are thought to begin as Oort cloud nuclei before they ever develop a visible coma. A nucleus is simply the solid body itself. In the inner Oort cloud, such nuclei remain inert and frozen. They do not announce their composition through activity. Their material properties must be inferred from comet science, from models of solar system formation, and from comparison with other icy bodies beyond the planets. This inferential method leaves room for uncertainty. Observations indicate that Oort cloud bodies are rich in ices mixed with rock and carbon-bearing compounds. It remains uncertain how wide the compositional variety is across the full population, and how strongly that variety reflects different birthplaces in the young solar system. Size also matters to composition, though mostly in how material is retained. Larger bodies can hold internal heat slightly longer in early history and may preserve layered structures or mixtures that smaller bodies cannot. Smaller ones may lose certain compounds more easily if they experience later heating during inward travel. But in the inner Oort cloud as a reservoir, most bodies are expected to remain relatively small by planetary standards. They are not miniature planets with active interiors and strong gravity. They are ancient fragments and frozen small worlds, shaped more by origin and storage than by ongoing internal evolution. This mixture of ice, dust, rock, and carbon-rich matter gives the inner Oort cloud a quiet material complexity. It is not a place of one substance repeated endlessly. It is likely a broad collection of preserved leftovers from multiple zones of early solar system history. Some ingredients may originate nearer the giant planets. Some may come from farther out. The reservoir gathers them together not by similarity of appearance, but by common fate. They are the bodies that are thrown outward and then retained in deep cold. Composition therefore becomes a kind of historical record. Each distant object may carry within it evidence of where and under what conditions it first formed. So the inner Oort cloud is not only a store of remote motion, it is also a store of ancient matter. Its unseen bodies are thought to be made of volatile ices, rocky minerals, dust, and carbon-rich compounds assembled during the solar system's beginning and preserved in long darkness. They remain frozen because distance protects them from the sun. They remain valuable because that protection may allow them to retain some of the oldest surviving material in the solar system. In the cold silence of the inner reservoir, matter from the age of formation rests in small scattered bodies, carrying a chemical memory older than any planet's surface. In the inner Oort cloud, preservation does not mean perfect stillness. The distant bodies stored there remain cold, dark, and far from the sun, yet time continues to act upon them. Change arrives slowly, often so slowly that it does not resemble change at all, but over immense spans even a frozen object in deep space is altered. The agents are not warmth, weather, or flowing water. They are radiation, tiny impacts, internal stresses, and the steady passage of millions and billions of years. The result is a form of quiet transformation, one that reshapes surfaces and perhaps even deeper layers without disturbing the essential cold silence of the region. Radiation is one of the most important of these agents. Space is not empty of energetic particles. Distant bodies in the Oort cloud are exposed to cosmic rays, which are high-energy particles moving through the galaxy, along with other forms of background radiation. These particles strike surface material and slowly change its chemistry. Molecules can be broken apart, new compounds can form, ices can become more complex and less pristine than they once were. Carbon-rich material may darken. Surface layers may gradually develop a processed crust, altered not by heat but by repeated particle damage over immense time. This is not a violent process. It is more like a slow rewriting of the outermost skin of the object. Such processing matters because the surface of a body is its interface with space. What lies below may remain more protected, but the exterior absorbs the long record of exposure. A fresh surface rich in volatile ice may, after enough time, become darker, chemically modified, and less representative of the untouched interior. This means that even objects stored in cold isolation do not preserve all parts of themselves equally. Their outer layers may carry the signature of deep time in a very different way than their inner material. The Oort cloud may therefore preserve ancient substance while also allowing its surfaces to age into something new. Tiny impacts contribute to this aging. The inner Oort cloud is extremely sparse, and collisions between major bodies are rare, but that does not mean surfaces are never struck. Small dust grains and minute fragments can still impact over long spans. Each event may be minor, but when counted across millions of years, such impacts can chip, roughen, and garden the surface. Gardening in planetary science refers to the slow stirring and reworking of the upper layer of material through repeated small impacts. In the Oort cloud, this gardening is expected to be far less active than on many closer bodies, but deep time allows even low rates to matter. A surface can be gradually broken, mixed, and retextured without any need for dramatic collision. This slow bombardment may also expose buried material in small patches while coating other areas with ejecta, the matter thrown out during an impact. The result is a complicated surface history even in an environment of extreme stillness. A body may appear inert, yet its outer layer can preserve countless tiny records of contact. Over time, these records blend into broader changes in texture, porosity, and reflectivity. Porosity means the amount of empty space within a material. Many small icy bodies are thought to be porous, more like loosely assembled mixtures than dense solid stone. Repeated impacts, even small ones, can compact some regions and fracture others, subtly changing how the surface responds to later heating if the body ever travels inward. Internal change may occur as well, though likely in a limited way for many objects. Some bodies may contain amorphous ice, a form of ice in which the molecules are arranged without the regular crystal structure of ordinary ice. Over time and under certain conditions, this material can shift into a more ordered state, releasing a small amount of heat. Radioactive elements within rocky material may also provide weak internal heating, especially early in a body's history, though in most small Oort cloud objects this effect is expected to be modest. The importance of such processes remains uncertain from object to object. They may not transform the body dramatically, but they can contribute to gradual internal settling, structural adjustment, or the retention and migration of trapped gases. These gases are important because distant icy bodies are not always simple frozen mixtures with fixed layers. As radiation and time alter near-surface chemistry, and as internal structure slowly adjusts, volatile compounds can move through pores and fractures. Some may freeze again in colder regions. Some may become trapped beneath hardened crusts. This can make the outer parts of a comet nucleus or Oort cloud body more complex than a single uniform block of ice and rock. The body becomes a layered record of exposure, storage, and slow reorganization. In the inner Oort cloud, all of this happens without visible activity. The processes are real, but their pace is so measured that the objects remain outwardly silent. Fracturing also belongs to this quiet evolution. Even in great cold, materials expand and contract in response to subtle changes, impacts, or internal rearrangement. Over very long periods, a body can develop cracks and zones of weakness. If it is a contact object, meaning two lobes joined together, or a loosely bound aggregate of fragments, it may be especially vulnerable to slow structural change. Some cometary nuclei observed closer to the Sun show signs of fragile assembly, suggesting that at least part of the Oort population may consist of bodies with delicate internal structure. In deep cold, that fragility can endure for long ages, but it does not imply complete permanence. A weak body may slowly settle under its own slight gravity, or respond to impacts by opening new fractures rather than by remaining unchanged. There is also the effect of long memory. The inner Oort cloud stores bodies not merely for thousands of years, but for spans comparable to the age of the solar system. On such timescales, even processes too slow to matter elsewhere become significant. A tiny chemical alteration repeated over billions of years becomes a transformed surface. A minute impact rate becomes a reworked crust. A subtle internal stress becomes a fracture pattern. This is why stillness in space must never be confused with the absence of history. The Oort cloud is quiet, but it is not timeless. Its bodies age, only in a manner suited to deep cold and enormous duration. Observations of comets that later enter the inner solar system support this general picture. Many comet nuclei appear dark, fragile, dusty, and chemically complex rather than bright and pristine. That does not prove that every Oort cloud body ages in exactly the same way, but it suggests that prolonged storage does not leave them untouched. It remains uncertain how much surface processing varies from one object to another, and how deeply these changes extend below the exterior. Yet the broader conclusion is clear. The inner Oort cloud is a repository of old matter that continues to evolve slowly under radiation, minute impacts, and internal adjustment. So the frozen darkness of the inner cloud is not a state of perfect preservation. It is a setting for extremely slow change. Radiation alters chemistry. Tiny impacts reshape the surface. Internal materials settle, fracture, and reorganize by small degrees. Over the age of the solar system, these quiet processes become meaningful. They do not erase the ancient nature of the bodies stored there, but they ensure that age leaves marks. In the deep stillness beyond the known planets, time continues its work, not by heat or motion, but by patience. The inner edge of the Oort cloud is one of the least certain boundaries in the solar system, far from the planets, beyond the known belt of large icy bodies, and beyond the region where familiar maps still name individual worlds. The distant populations of small objects do not arrange themselves into a neat sequence of sharp borders. Instead, one remote domain begins to resemble another. The inner Oort cloud, if it exists as a distinct reservoir, appears to fade inward through a broad zone where definition becomes difficult. Here the problem is not simply distance, it is classification. Astronomers can describe the general idea of the Oort cloud with confidence, yet the exact point where its inner portion begins remains uncertain, because distant bodies are known mostly through theory, through a small number of extreme observations, and through the long-term behavior of comet orbits rather than through direct survey of the region itself. This uncertainty arises partly because the Oort cloud is not visible as a structure. No telescope sees a glowing shell that can be traced inward until it becomes a different population. The region remains inferred, which means its boundaries must also be inferred. Astronomers ask how strongly an object is bound to the Sun, how easily outside influences can disturb its orbit, and whether its path belongs more naturally to the distant comet reservoir or to other trans-Neptunian populations. Trans-Neptunian simply means beyond Neptune. In the inner edge region, those distinctions do not always produce a single clear answer. An orbit may share characteristics with more than one category. One source of difficulty is the scattered disk, a distant population of icy bodies whose elongated paths have been strongly shaped by Neptune. Some of these objects travel far from the Sun, though not usually as far as the main Oort cloud is thought to extend. Others belong to what are often called detached objects, whose orbits are remote and unusual enough that their present relationship to Neptune is weaker or more indirect. Between these populations and the proposed inner Oort cloud lies a wide grey zone. A body can seem too distant and too weakly connected to the giant planets to be comfortably placed in the scattered disk, yet still too near or too flattened in orbital pattern to look like a classic member of the Oort cloud. The shape of the inner region adds to the challenge. The outer Oort cloud is usually described as roughly spherical because its members approach the inner solar system from many directions. The inner Oort cloud may be less spherical and more flattened, retaining a stronger memory of the plane in which the planets formed. If that is true, then the inward transition may not only be a change in distance, but also a gradual change in geometry. The broad sphere of the outer reservoir may taper inward toward a more disk-like arrangement, though still one far thicker and more distant than the familiar planetary plane. This means there may be no single inner surface to cross. Instead, the cloud may slowly lose its rounded distribution and merge into other far-flung populations through changing orbital orientation and binding strength. Distance estimates reflect this uncertainty. Different studies place the inner boundary of the inner Oort cloud at different locations, sometimes several thousand astronomical units from the Sun, and sometimes farther out. These differences often arise because different definitions are being used. One model may define the boundary by distance alone. Another may define it by the dominant source of perturbation, meaning what most strongly changes an orbit over time. Another may define it by the likelihood that a body can later become a long-period comet. Each approach highlights a real aspect of the region, but none can draw a universally accepted line across a structure that has never been observed directly. The role of Neptune complicates the picture further. Closer in, the giant planets, especially Neptune, remain important in shaping orbits. Farther out, the Oort cloud becomes the realm where galactic tides and passing stars matter increasingly over long times. The inner edge lies between these regimes. It is therefore not only a spatial transition but a dynamical one. Dynamical here refers to what governs motion across time. At the uncertain boundary, some objects may still carry the strong signature of planetary scattering, while others may already belong more fully to the distant reservoir whose long-term evolution depends on the galaxy and on stellar encounters. The two influences overlap, and that overlap is one reason the boundary resists simple description. Observational limits deepen the uncertainty. The most remote known objects are hard to detect because they are faint, slow moving against the sky, and visible only when current telescopes can distinguish them from countless background sources. Surveys are incomplete and favor certain brightness levels and orbital configurations. This means that the discovered sample of distant bodies is not a perfect map of what exists. Some classes of objects may be undercounted simply because they are difficult to find. As a result, the apparent structure of the inner edge may partly reflect the limits of observation as much as the true arrangement of the outer solar system. Even the name inner Oort cloud can suggest more precision than the evidence allows. It is a useful theoretical phrase, but it should not imply a sharply bounded chamber nested cleanly inside the outer cloud. It is better understood as a proposed inner domain of more strongly bound distant bodies whose exact beginning remains debated. Observations indicate that some very remote objects may belong to such a domain. It remains uncertain how broad that domain is, how much it overlaps with detached populations, and whether all researchers would place the same objects within it. So this inward-facing edge of the Oort cloud remains one of the most elusive regions in solar system science. It is remote, faint, sparsely populated, and difficult to classify. It may begin closer in than some estimates suggest, or farther out than others prefer. It may retain a flattened shape before merging into a more spherical outer structure, and it may overlap significantly with other distant populations whose histories and motions partly resemble its own. In this uncertain boundary zone, the Oort cloud does not present itself as a clearly walled reservoir. It emerges only gradually from the wider outer solar system, and the exact moment of emergence remains hidden in darkness, distance, and the limits of present observation. The bodies of the Oort cloud do not begin their history in the distant darkness where they now reside. In the current scientific picture, they form much closer to the young sun, within the broad region where the giant planets are assembling, and where countless smaller icy and rocky objects move through a dense and active early solar system. This origin matters because it explains why the Oort cloud is not a separate creation beyond the planets, but a remote afterlife of material once belonging to the inner part of the outer solar system. The cloud is made not by local formation in deep interstellar cold, but by outward scattering, a process in which small bodies are thrown away from the young planetary region and later retained at immense distances. In the beginning, the solar system is not arranged as it appears today. It is a rotating disk of gas and dust around the newborn sun, often called the solar nebula. Within this disk, tiny grains collide and stick. Over time, they grow into larger clumps, then into planetesimals, the small bodies that serve as the building blocks of planets. Some remain small, some merge into larger worlds, beyond the warmer inner regions, where volatile materials can remain frozen. These planetesimals contain abundant ice mixed with rock and dust. They are the ancestors of many later comets, and of much of the distant small body population. As the giant planets begin to grow, the environment changes profoundly. Jupiter, Saturn, Uranus, and Neptune do not merely occupy space. Their increasing masses allow them to reshape the motion of nearby smaller bodies through gravity. A close gravitational encounter can alter the path of a planetesimal sharply, sometimes by only a little, sometimes by a great deal. In the crowded young solar system, such encounters are common enough that a vast number of small icy objects do not remain where they form. They are redirected, accelerated, or flung outward. This is the beginning of the Oort Cloud story in physical terms. The cloud is born from displacement. The word scattering describes this process well, because the small bodies are not guided outward in an orderly migration. They are redistributed through repeated gravitational kicks from the giant planets. A planetesimal passing near a growing giant planet can have its orbit stretched into a much more elongated shape. Its nearest point to the Sun may remain in the planetary region for a time, while its farthest point is pushed dramatically outward. If it survives further encounters without being ejected completely from the solar system or driven into a planet or the Sun, it can end up on a path that reaches into vast distances. Many such paths are unstable at first, continuing to cross the giant planet region and inviting more encounters. But over time, a fraction of these bodies are lifted into orbits whose distant ends move so far out that the planets no longer dominate them directly. Jupiter is especially important in this early scattering because of its great mass. Its gravity is strong enough to redirect small bodies very efficiently. Saturn also contributes substantially, and Uranus and Neptune play major roles in shaping the colder outer populations. The exact share of responsibility varies from one model to another, but the general principle remains firm. The giant planets act as gravitational engines that throw leftover planetesimals outward. Some of those bodies are lost forever into interstellar space. Some remain in flattened distant populations beyond Neptune. Some, through a combination of planetary scattering and later external influences, become part of the Oort Cloud. This origin explains why the cloud may contain material from more than one birthplace. Bodies that form in somewhat different parts of the young outer solar system can all be scattered outward into the distant reservoir. Their compositions may therefore preserve a range of early conditions rather than a single uniform environment. Some may form nearer the region of Jupiter and Saturn, where temperatures and chemical conditions differ from those farther out near Uranus and Neptune. Others may come from still colder zones. The Oort Cloud gathers these varied remnants not because they form together in one far outer nursery, but because planetary scattering sends them toward the same remote fate. The process is not completed in a single event. A body may undergo multiple encounters before finding a long-term distant orbit. Each passage near a giant planet can revise its trajectory. Some objects are pushed farther out with each encounter, some are sent inward again, some are lost. What matters for the future cloud is that a portion of this scattered population eventually reaches distances where outside influences, especially galactic tides and passing stars, can raise their periheliae, meaning their closest points to the Sun, enough to keep them from returning frequently to the planet region. Once that happens, the body can remain stored in the distant cloud for immense spans. But at this stage of the story, the crucial fact is simpler. The first push comes from the planets. That makes the Oort Cloud a record of planetary formation as much as a reservoir of comets. Its existence, if described correctly, reflects a solar system that once contains far more small bodies in the giant planet region than it does now. The cloud represents the leftovers of construction, material not incorporated into planets and not fully expelled from the Sun's domain. In that sense, it is a graveyard of failed building blocks, though not a lifeless one. These are ancient survivors of a violent sorting process that accompanies the growth of the giant planets. The early solar system is therefore much more crowded and dynamically active than the calm planetary arrangement known today. Orbits cross. Massive bodies migrate to some extent in many models. Small planetesimals are thrown onto new paths in enormous numbers. The present distant cloud is the long-term consequence of this youthful instability. It forms because the giant planets do not simply settle into place and leave the remaining material alone. They clear, stir, and expel. The Oort Cloud is one of the places where that expelled material remains bound. This origin also clarifies why the cloud does not form as a disk like the planets themselves. Despite coming from the same general early system, the initial scattering begins in the flat solar nebula, but later external influences gradually reshape the distant orbits into a more spherical distribution. At the moment of scattering, however, the paths still carry the memory of planetary encounters. The bodies are launched outward from a crowded disk-like formation zone, and only later become part of the distant cloud. Their first step into that future is not quiet storage, it is gravitational exile. So the bodies of the Oort Cloud begin not in the silence of the far outer dark, but in the active young region of giant planet formation. They are born as ordinary planetesimals within the early solar system, then thrown outward by repeated encounters with the growing massive planets. Some are lost, some remain closer in, some survive on distant paths that later become part of the remote reservoir around the Sun. The Oort Cloud is therefore not an original outer shell waiting from the beginning. It is a scattered inheritance, made from ancient small bodies cast outward during the formative disorder of planetary birth. The Oort Cloud is not shaped by the giant planets alone. Its early structure may also depend on the environment in which the Sun itself is born. The leading picture in modern astronomy is that stars usually form in groups inside large clouds of gas and dust. The Sun is therefore unlikely to begin its life in complete isolation. It more likely emerges among many neighbouring young stars, sharing a crowded stellar nursery where distances between stars are much smaller than they are in the Sun's present galactic neighbourhood. This early setting matters because the same small icy bodies being thrown outward by the giant planets are not entering an empty background. They're entering a region where other stars are nearby, and where outside gravitational influence is stronger and more frequent than it is later. A stellar nursery is not a single neat cluster with one universal shape. It is a birth environment, a place where many stars condense from the same giant molecular cloud, meaning a cold interstellar cloud rich in gas and dust. Within such a region, young stars may remain near one another for a time before the group slowly disperses. During that early period, each forming planetary system exists inside a crowded gravitational landscape. For the young Sun, this could have important consequences. Bodies scattered outward by Jupiter, Saturn, Uranus, and Neptune would not only feel the Sun and the planets, they might also be influenced by neighbouring stars passing much more closely than stars usually do today. This possibility offers a natural explanation for part of the Oort Cloud's deeper structure. If the Sun forms in a crowded stellar environment, then outward scattered planetesimals can have their orbits altered early, while the cloud is still coming into being. A nearby young star does not need to capture these bodies or strike the solar system directly. It only needs to pass close enough for its gravity to raise the perihelia of some scattered objects, lifting their closest approach to the Sun away from the region of the giant planets. Once that happens, those bodies are less likely to return for repeated planetary encounters. They can be stored more effectively in distant orbits instead of being thrown out of the solar system altogether. This mechanism is especially important for the formation of a deep inner reservoir. A crowded birth environment can help create an inner Oort cloud by trapping some scattered bodies early before they are lost. The giant planets send material outward, but nearby stars in the birth cluster may help secure part of that material into more stable distant storage. In this picture, the inner cloud does not emerge only from the later slow action of galactic tides. It may begin its life under stronger local stellar influence while the Sun is still young and surrounded by sibling stars. This would make the deeper Oort reservoir not just a product of planetary scattering, but also a product of the Sun's birthplace. The role of the birth cluster may also help explain why the Oort cloud can survive at all. During the era of giant planet formation, many scattered planetesimals are vulnerable to complete ejection. Jupiter in particular is very effective at throwing small bodies onto escape paths. If the solar system evolved in isolation from the beginning, the balance between retention and loss might produce a different distant structure than the one inferred today. A denser stellar environment changes that balance. Some bodies that might otherwise be ejected may instead have their orbits lifted into long-term storage. The result is a cloud shaped partly by rescue through disturbance. External gravity does not only remove, at the right time, it can preserve. That preservation would not be uniform. A crowded stellar nursery introduces repeated encounters from different directions, with different masses, speeds, and closest distances. The structure that emerges is therefore not expected to be perfectly smooth. Some parts of the forming cloud may be influenced more strongly than others. Some orbits may be lifted into the deep reservoir. Others may be removed entirely. Some may remain in more flattened distributions. The details depend on the number of neighbouring stars, how long the Sun remains in the cluster, and how close the most important encounters become. Observations indicate that a clustered birthplace for the Sun is plausible and likely. It remains uncertain exactly how crowded that environment is and how strong its specific effects are on the final architecture of the Oort cloud. There are also broader clues that support the importance of a stellar nursery. Certain radioactive isotopes present in the early solar system suggest that the Sun forms in a region influenced by nearby stellar activity. Isotopes are forms of an element with different numbers of neutrons. Some short-lived radioactive isotopes found in ancient solar system material are often interpreted as signs that the young Sun forms near other stars, perhaps even near massive stars whose lives are brief and energetic. This does not prove the exact layout of the birth cluster, but it supports the broader idea that the solar system begins in company rather than solitude. If so, then the Oort cloud's earlier shaping takes place in a more active local environment than the one the Sun inhabits now. The clustered beginning also helps explain why the outer solar system may preserve traces of events that no longer occur. Today, the Sun moves through a comparatively diffuse stellar neighborhood. Passing stars are rare on short timescales and generally distant. The early solar system may be very different. For a limited era, the young Sun could experience closer and more frequent stellar passages, making the birth period a special window in which distant scattered bodies are reorganized efficiently. Once the cluster disperses, that stronger phase of shaping would end, leaving the cloud to evolve more slowly under the gentler background influence of the Milky Way and occasional later stellar encounters. This means the Oort cloud may contain a layered memory of timing as well as distance. Some parts of its structure could reflect very early events tied to the Sun's nursery, while later modifications come from the broader galactic environment. The deeper inner reservoir, in particular, may owe part of its existence to early cluster conditions. Without that crowded birthplace, the distant store of securely bound bodies might be smaller or differently arranged. The cloud becomes, in this view, a remnant not only of planet formation but of the Sun's first social environment among other stars. Even the contrast between the solar system today and its origin becomes sharper through this lens. The present Sun appears isolated enough that its planets and small bodies seem like a self-contained family. But at birth, the Sun may belong to a community. Its scattered planetesimals travel outward through a neighborhood in which other young stars also possess gravity, perhaps also their own disks and their own building materials. The early Oort cloud is therefore not formed in emptiness around a solitary star. It is assembled in a crowded stellar setting where outside influence is woven into its earliest history. So the Sun's birthplace may be essential to understanding why the Oort cloud takes the form it does. The giant planets provide the outward scattering, but the early cluster environment may help convert some of that scattered population into a lasting distant reservoir. Nearby young stars can lift, preserve, remove, and reshape orbits while the cloud is still forming. In that sense, the Oort cloud carries evidence not only of the solar system's internal formation, but of the crowded nursery in which the Sun first begins its life among many other stars. At the inward-facing frontier of the Oort cloud, the solar system begins to recover forms that can be mapped more directly. The distant reservoir does not end in a visible boundary, yet the character of the region changes as one moves conceptually inward from the hidden cloud toward the outer worlds beyond Pluto. The great spherical and weakly bound domain of the Oort system gradually gives way to populations that are flatter, more strongly connected to the plane of the planets, and more accessible to observation. This is still the deep outer solar system, still a realm of cold, darkness, and immense separation, but it is no longer the same kind of distance. The Sun's hold becomes less uncertain. The influence of the giant planets becomes more recognizable. Individual objects begin to emerge from theory into direct discovery. This inward frontier is best understood as a transition from the inferred to the observed. In the Oort cloud, the population is known mainly through comet orbits and dynamical models. Closer in, beyond the orbit of Neptune and beyond Pluto, astronomers can detect actual bodies and follow their motion over time. Their orbits are still long and remote, yet they can be measured, named, and compared. Some belong to the Kuiper Belt, a broad disk-like population of icy bodies beyond Neptune. Others occupy the scattered disk, where elongated orbits carry them much farther from the Sun under the continuing historical influence of Neptune. Still others are detached objects, distant worlds whose paths suggest a weaker present connection to the giant planets. These populations do not belong fully to the Oort Cloud, yet they stand near its uncertain inward approach. What changes here is not only visibility, but geometry. The Oort Cloud, especially in its outer reaches, is treated as a roughly spherical reservoir surrounding the Sun. The outer solar system beyond Pluto is not like that. It retains the flattened memory of the original solar nebula, the disk from which planets and smaller bodies form. Even when individual objects travel on tilted and elongated paths, the overall distribution remains much more disk-like than the broad enclosing cloud farther out. This return to flattening is one of the clearest signs that the solar system is moving inward toward the more familiar architecture of its planetary origin. The difference in binding also becomes clearer. Bodies on the inward side of the Oort frontier are still distant, but many of them are more firmly tied to the Sun and more clearly linked to the gravitational history of Neptune and the other giant planets. Their orbits may be stretched, yet they are not usually held at the threshold of loss in the same way as members of the far outer cloud. A detached body, such as Sedna, for example, occupies a path so remote that it seems to stand near the conceptual bridge between the inner Oort cloud and the known detached population. It does not by itself define the boundary, but it shows how the outer solar system contains objects that blur familiar categories. Some bodies appear too distant to belong comfortably to the ordinary scattered disk, and yet not distant enough to serve as direct representatives of the main Oort reservoir. This grey zone is where the hidden cloud approaches the observable outskirts. Even here, emptiness remains the dominant physical condition. The region beyond Pluto is not crowded in any everyday sense. The known dwarf planets and smaller icy bodies are separated by huge distances, and most of the volume is dark space. Yet compared with the Oort cloud, this outer frontier feels more tangible. The Sun is still faint, but less diminished. Motion is still slow, but more measurable within modern astronomy. Objects can be revisited by telescopes. Their surfaces can be studied through reflected light. Some can even be reached by spacecraft. As Pluto and Arakoth show in different ways within the broader trans-Neptunian realm, no such direct approach has yet been possible for the Oort cloud itself. The inward frontier is therefore not merely a change in orbital statistics, it is a change in the kind of knowledge that astronomy can achieve. This frontier also carries an important historical meaning. The Oort cloud is made from bodies scattered outward from the young planetary region. The populations beyond Pluto preserve intermediate outcomes of that same ancient process. Some material is thrown far enough to become part of the distant comet reservoir. Some remains closer in, reshaped, but not fully lifted into the hidden cloud. The outer solar system beyond Pluto therefore acts as the visible residue of the same early scattering history that produces the unseen Oort domain. It is the nearer remnant of a broader outward dispersal, one that still carries the imprint of the giant planets and of the disk in which everything begins. Yet the transition remains uncertain in detail. No universally accepted line separates the innermost Oort cloud from the farthest detached populations. Distance alone does not solve the problem, because similar distances can still host different orbital histories. Shape alone does not solve it, because the geometry of the transition may itself be gradual. Dynamical behavior helps, but even that leaves room for overlap. Observations indicate that the solar system's remote frontier is not organized into sealed compartments. It is better described as a sequence of changing regimes, where one form of orbital life shades into another. The Oort cloud recedes inward by losing its full spherical remoteness. The known trans-Neptunian region emerges by recovering the flatter and more directly observed structure of the outer planetary system. At this inward edge, the solar system begins to feel less abstract. Names return. Pluto is no longer only a cultural marker from an earlier age of planetary classification. It becomes part of a larger landscape of distant, icy worlds that can be placed on charts and studied individually. Neptune remains remote, yet its past gravitational power becomes legible in the orbital patterns of bodies beyond it. The hidden cloud no longer surrounds the imagination as an unseen sphere. Instead, the mind arrives at a frontier where distant matter still belongs to deep time and deep cold, but where the solar system has become readable again through actual objects. So the inward-facing frontier of the Oort Cloud is not a wall, but a soft return to the known. The invisible distant reservoir yields gradually to the outer populations beyond Pluto, where the sun's authority is stronger. The original disk-like order becomes more apparent, and astronomy can once more point to individual worlds rather than to inferred swarms. The darkness remains, the cold remains, the immense scale remains. Yet here, at the threshold between hidden cloud and observable outskirts, the solar system begins to take on familiar form again, and the long unseen reach beyond Pluto narrows into a distant landscape that can at last be partially seen. Far beyond the reach of ordinary sight, the Oort Cloud remains a place known through consequence rather than image. It has no photographed horizon, no direct survey, no clear rim shining in the dark, yet its presence settles quietly into the structure of the solar system. It marks the farthest extent of a long history that begins near the young sun, passes through the growth of giant planets, and ends in a remote sphere of scattered icy remnants held by the weakest thread of gravity, from the outermost fading edge inward through the hidden reservoir. The region reveals the solar system in its widest form. It shows that the sun does not govern only the bright worlds and mapped bodies near the center. Its influence reaches outward into a population so sparse and so cold that emptiness becomes its defining condition. There, time moves by orbital ages, surfaces change by patience, and the galaxy itself begins to leave gentle marks on distant motion. The Oort Cloud also preserves a quiet lesson about origins. Its bodies are not strangers formed beyond the planets in complete isolation. They are ancient leftovers of formation, thrown outward, lifted, stored, and altered over billions of years. Some later return as long-period comets, carrying frozen material inward from a realm that no instrument has yet seen directly. Most remain in darkness, scattered so widely that the cloud can be inferred but not observed as a whole. In this way, the unseen region beyond Pluto becomes less a blank emptiness and more a distant memory field around the sun. It is a record of formation, scattering, storage, and survival. It is the solar system at its most extended and least visible, fading outward into the wider Milky Way while still remaining, however loosely, the sun's own far domain.